Hello everyone, my name is Jade. Today I'll be presenting a comparative analysis of K-means and hierarchical clustering on global women's education across wealth quintile using Orange software. K-means and hierarchical clustering are two popular unsupervised machine learning techniques used to group similar data points together. K-means clustering partitions data into predefined number of clusters, assigning each data point to the nearest cluster center. While hierarchical clustering, on the other hand, creates hierarchy of clusters, starting from individual data points and merging them into larger clusters based on similarities. Both methods can be used to identify patterns and trends within the data. Now that we have a better understanding about K-means and hierarchical clustering, let's move on to our problem statement. Despite global efforts, disparities in young women with secondary or higher education persist across countries and wealth quintiles. Our study aims to uncover patterns and trends in educational attainment using two clustering methods, K-means and hierarchical clustering. By analyzing this data, we hope to identify socioeconomic factors influence education and inform strategies for equitable access to quality education. To provide context, previous studies by Kaushik and Mathur, Gupta, Sharma, and Akhtar, and Chen and others have explored these clustering techniques. They highlight the strengths and weaknesses of each method and even proposed a hybrid approaches like hierarchical k-means to overcome traditional limitations. These insights guided our methodology in applying clustering to global educational data. For our analysis, we used data from Demographic and Health Survey, focusing on young women aged 15 to 24 with secondary or higher education across wealth quintile. Two clustering methods, K-means and hierarchical clustering, are applied to group countries based on their similarities in educational attainment. This dataset includes 215 observations, including one categorical variable, which is the country name, and 7 numerical attributes such as survey year and educational percentage across wealth quintile. We prepared this data through steps like nominal data coding, removing invalid entries, and standardizing numerical values to ensure consistency across variables. To make this even clearer, let's break it down step by step. The country name attribute is represented by numeric code. In this technique, elements are assigned ordinal values based on each country. The code is presented in Figure 2. Data cleaning remove noise data or invalid data. In this step, the total attribute will remove, fixing the survey year as numeric since it is the same as the survey name, which indicates the year the survey was conducted. The clean data has shown in Figure 3. The dataset was standardized to bring the numerical variables to a common scale. Standardization transformed the data by subtracting the mean and dividing by the standard deviation, ensuring that all variables have the similar influence to the clustering algorithm. Figure 4 shows the standardized data. This step ensures the data was prepared and streamlined for cluster analysis, allowing for the identification of meaningful group or clusters. Now let's explore K-means clustering in Orange software. After we load our data to a file widget, connect the file widget with K-means. K-means requires us to specify the number of cluster, but in Orange, we can also ask to find the right number of cluster using Silhouette. Silhouette scoring reports how well each data point on average fits into its designated cluster. The higher the score, the fewer data points we have where clustering membership is not clear. Means the highest score suggests the optimum number of clusters. In this case, it's 2. Now let's observe the 2 cluster on Silhouette plot. A positive score indicates that the object is well matched to its own cluster. A negative score suggests that the object may be assigned to the wrong cluster. In our case, we don't have negative score. It suggests good clustering. We can also observe the clustering in scatter plot. The separation between clusters suggests that the data was successfully divided into two distinct groups.
Cluster 2, colored red. Countries in this cluster exhibit high levels of educational attainment among young women across all wet quintiles. The progression is evident with an average of 32.45% in the lowest quintile and increasing consistently to 87.14% in the highest quintile. This includes countries from diverse regions, including Latin America, Southeast Asia, and some parts of Africa and Europe. Cluster 1, colored blue. This cluster represents countries with low educational attainment across wealth quintiles. The average starts at a very low 3.73% in the lowest quintile and rises to only 35.40% in the highest quintile. This includes countries primarily from sub-Saharan Africa, South Asia, and some parts of Southeast Asia.
Now let's explore hierarchical clustering in orange. Using our standardized data, we load our data to a file widget. Now connect file widget with the distances. Since hierarchical clustering requires distance matrix on the input, we use the Euclidean distance matrix. Let's pass out the data to the hierarchical clustering widget. The widget displays a dendrogram, a tree-like clustering structure. Each node represents an instance in the dataset. We already know that 2 is the optimum number of cluster. We choose 2 clusters. The dendrogram reveals 2 primary clusters, with one cluster containing a single observation, likely an outlier or an unique data point, and the other cluster encompassing the majority of observations.
Using MDS plot generated using Orange, it visualized the relative dissimilarity between data points in a two-dimensional space. The dense cluster of red points, cluster 1, indicates a group of highly similar data, while the single blue point in cluster 2 is an outlier, positioned far from the main cluster, signifying it is significantly dissimilar from the other data points. The gray line connecting the red points suggests relationship of similarities within the data cluster, highlighting its cohesive nature, while the lack of connections of the blue point underscores its isolation.
The result of k-means clustering on standardized data differ from those hierarchical clustering on the same standardized dataset. While k-means formed two well-defined clusters with balanced distribution, hierarchical clustering produces an uneven clustering structure, with one cluster containing a single observation and the other encompassing the majority of the dataset points. This discrepancy highlights the sensitivity of hierarchical clustering to linkage methods and distance metrics. Let's try again hierarchical clustering without standardizing the dataset in orange. Again, choosing Euclidean distance metric, the dendrogram now shows two main clusters. This result suggests that the dataset naturally divides into a large homogeneous group and smaller, more distinct group, potentially driven by unique patterns in the variables. The separation highlights meaningful differences that warrant further investigation into the characteristics defining each cluster. We pass those clusters to MDS, which shows a 2D projection of data instances, colored by cluster label. Two clusters are clearly distinguished. Cluster 1, colored red, predominantly occupies one region of the plot, while cluster 2, colored blue, occupies another with minimal overlap. This indicates that the data separates well into two distinct groups, suggesting a strong cluster structure. The separation likely reflects meaningful differences in the underlying data attributes, validating the clustering method used. Now we use the scatter plot from the latest hierarchical clustering result to compare with the scatter plot from the previous k-means clustering. The comparison of two scatter plots reveal that the clustering results are identical, with the same grouping patterns and clustering assignments observed in the both plots. In our interpretation, K-means is sensitive to the scale of variables. Standardizing the data ensures that each variable contributes equally to the clustering process. Regardless of its original scale, the result of two well-defined clusters is expected because the standardization prevents variables with larger magnitudes from dominating the distance calculations. The result of only one observation in one cluster and the rest in the other suggests that hierarchical clustering may still be sensitive to nuance in the data. Even after standardization, this could be due to the choice of distance metric or linkage criterion. When using non-standardized data on hierarchical clustering, the results aligns with the K-means result on standardized data. This suggests that the hierarchical clustering approach you used might inherently handle non-standardized data. Well, in this case, possibly because one variable dominates the distances, calculations, and masks the variability in others. Comparing the two results, the alignment between K-means on standardized data and hierarchical clustering on non-standardized data implies that the latter might not require standardization in specific cases, especially when dominant variables naturally reflect meaningful distances. However, this could also indicate a potential imbalance in your data that hierarchical clustering is picking up without standardization. The primary limitation of this study is the sensitivity of clustering methods to data pre-processing such as standardization, which can significantly alter results and complicate comparisons. Variables with larger scales such as highest quintile and fourth quintile may dominate the clustering process, especially in hierarchical clustering when the data is not standardized. Additionally, this study relies on distance-based methods that assume homogeneity and may not capture complex or overlapping cluster structures, particularly in correlation among wealth quintiles variables. The choices of the number of cluster in K-means and linkage methods in hierarchical clustering also introduce subjectivity. In conclusion, the use of K-means and hierarchical clustering proves valuable in identifying patterns and trends in young women's education. However, accuracy and reliability of these insights depend heavily on careful data pre-processing and application method selection. Without these steps, cluster analysis may produce misleading or inaccurate results, underscoring the need to a thoughtful and rigorous approach, ensuring meaningful outcomes in education research. Thank you everyone for listening. Have a good day and Merry Christmas.